What's going on, everybody? It's Mr. Gustin back in the physics classroom.
Happy Wednesday.
Happy Wednesday with Nico. All right, Nico, get out of here. She forgot her charger in class thing. Folks, today we're talking about torque and we're talking about balancing. So let's go through two different things. We'll do a practice problem and we'll go ahead and do a little demonstration about balancing so that we get a sense of what it is. So in class, we've been balancing some things. We snapped a meter sticking down on a pivot point just to see how things are balancing. But let's go ahead and look at some of these awesome devices I have in the classroom, and we call them hook sticks. I call them a hook stick because I don't really know what else to call them, because that's what they are, is a stick with hooks on it. Now, this stick is not perfectly level, so I'm going to go ahead and level it by taking a very light mass and hanging it from the side that is raised. That doesn't work. Let's start in here. Maybe this will work. And that's pretty balanced, okay? So now it's balanced, it's not rotating, and if it's not rotating, it's also not accelerating rotationally. We've got a couple of different points on this stick that I want to point out. The first point I want to point out is called the pivot, or the axis of rotation. The pivot is the location that is fixed. So far, all the motion that we've seen in this class has been single objects or two objects moving together. And that means, like, if I dropped a ball, the whole ball, all the particles in the ball fell. If I pushed a box across the floor, the entire box moved across the floor. That's what we've seen so far. This unit in rotation, we're actually going to see objects that don't all move the same distance, don't all move together. We're going to see objects that have a fixed point and objects that will rotate their atoms, their molecules, around a fixed point. We call that fixed point the pivot point, the axis of rotation. Your teachers may call it different things. I'm going to call it the pivot this year, okay? This is my pivot. The other point on this beam that we have are what are called lever arms. And lever arms are distances, lengths of an object between the pivot point and some point on that object where a force is being applied. We call this the lever arm, and we denote it with the letter R. We'll show this more on the board here in a second. But here's the thing, it's balanced. If I go ahead and take a mass, a heavy mass, and I hang it right from the middle of this board, right underneath the pivot point, you notice that the board does not rotate. It does not unbalance the board. Here's our first takeaway. Forces that act at pivot points do not produce rotation. They do not produce what we call a torque on the system. There's definitely a force pulling down. The force from this rod is pushing up more, holding it steady up and down linearly, but not rotationally. This force does nothing, or this weight does nothing. Now, if I go ahead and I move this mass over here, 2 hooks away, roughly 20 centimeters, what we see is a crazy amount of rotation. All right, let's rebalance this thing. Let's put this here. Let's put this here. Is it going to stay? It doesn't even want to stay. It wants to slide off. Okay, well, let's do this. Putting a 1 kilogram mass 20 centimeters away obviously wants to make this board rotate. And it rotates so much that the mass falls off. So I want to go ahead and try to balance this out. So I'm going to put a different mass, a 500 gram mass over here. And we can see it's still not balanced. Let's put a 500 gram mass here. It is still not balanced. It's getting more balanced. It's more steady than it was before, but it's still not balanced. Let's go ahead and move it up this way. I've got again, 1 kilogram mass and a 500 gram mass. So, a factor of 100%. So this is a 1 kilogram mass and a ½ kilogram mass. Still not balanced, so we're going to keep moving. Ooh. And there we go. Now it's balanced. Let's look at this relationship. So we said that this mass here is 1 kilogram, and this mass over here is ½ kilogram. Let's look and see how far apart they are. From the pivot point, this is 10 centimeters. Each hook is 10 centimeters. So 20 centimeters away from the pivot point, And over here I see 1, 2, 3. This is 40 centimeters away from the pivot point. There's an interesting relationship here. It's clear that if I am, my mass and my distance, or my force and my distance, in this case the force of gravity, are kind of in this weird ratio, where if something is heavier, it needs to be closer to the pivot point for things to balance out, and objects that are lighter are further from the pivot point in order for us to reach this rotational equilibrium. And this relationship between force and distance, we call it torque. It's not just that forces cause things to rotate, it's that torques do. Not forces, because we see forces that act at pivot points don't cause rotation. We need to see a force away from the pivot point. And so that's what I am seeing here. Let's go to the board. Let's take some notes, all right? We're going up here. Let's get this definition written down, and let's go ahead and get some of this schematic stuff written down, all right? We call this the lever arm. I'll let you go ahead and pause the video, take some notes, write this stuff down in your notes if you need to, but this is just the definition, what I call rotational force or torque. An example of this problem that we just saw, some labels of some very obvious and kind of things that we see regularly in different rotational torque problems. And then how I define what rotation is caused by, right? Rotation is caused by forces acting away from the pivot point, and we call this torque. Now, what we'll also see is that it's not just any force acting away. Direction of the force matters, right? If I go ahead and I push on this stick from the side, it's not going to cause rotation. Or if I go ahead and pull on this stick out here, it's not going to cause rotation. So there's definitely some amount of perpendicularity, the idea that the force needs to be acting in a way that will cause rotation. We call that a perpendicular force, or some perpendicular component of force, but we can cover that later. For now, the basics are forces that act away from a pivot point cause objects to rotate or change their rotational motion. Speed up, slow down. That's what we see here, okay? And then generally speaking, we've got a couple directions. So we have the counterclockwise direction. And convention says counterclockwise is positive. You know I'm not a big fan of like, this is always positive, this is always negative. I'm not a fan of that. But just so you all are aware, like textbooks and convention, counterclockwise is the positive direction, and clockwise rotation is a negative direction if you read a textbook. That's not how I do things. It's not what I'm concerned about. I'm more concerned about you understanding that forces and torques in one direction will work against forces and torques in the other direction as we solve for net torque expressions, okay? First things first, let's do one small example before we do a bigger example. One small example will be our hook stick. Our hook stick looks like this. There was a FG from the 1 kilogram mass, and then twice the distance away, there was an FG from a 0.5 kilogram mass. This is what we saw. Now, two forces were missing. If this is my system, I have to think to myself that there are some things missing, right? If this were the only, if these two things were the only forces acting on my system, this object would be in free fall. It wouldn't be rotating, but it would be falling straight to the ground. So there must be some other force there, and there was. There was the force from the pin. There was a force from the rod supporting this thing. And I can't forget that. I have to remember that the rod itself is supporting both the 1 kilogram and the half kilogram mass. And to be honest, it's also supporting the weight of the stick. But I haven't drawn the weight of the stick. So where is the weight of the stick located? The weight of the stick is located at what we call the center of mass. FG for the center of mass. The center of mass is the average location of the mass of the stick. And for uniform objects like perfectly rectangular wooden sticks, it's right in the middle. All right, so this is a complete FBD. This is the complete force diagram for everything acting. And I can go ahead and write a net force equation for this, for the vertical direction, and I can go ahead and write a net torque expression for this. Let's go ahead and write the net force equation first. It's something we're familiar with. So let's think about the net forces. F net in the y direction, it's not accelerating up or down, so it's 0 newtons. Let's think. All the forces up, we have the F rod, minus all the forces down. So let's subtract them. Minus Fg from the 1 kilogram force, minus Fg from the center of mass, minus Fg from the 0.5 kilogram mass. This is my F net in the y direction. All of these forces are balanced out. I could probably figure out what these two forces are, mg's from the masses. That's pretty easy. I could probably throw the board on a scale and figure out that mass. Pretty easy. I could use all three of those to find the force of the rod upward. I can do all my normal MA calculations from this. This is a blast from the past. And it hopefully will help us as we go into torque. Let's now think about rotational motion and write a net torque expression. So net torque, torque is a vector just like force is. And in this case, there is no rotation or changing rotational motion. So net torque is 0 Newton meters. That's not joules, it's not energy, it's torque. And it's equal to all of the torques one way, counterclockwise, minus all the torques the other way, clockwise. So I see a torque from the force G of the 1 kilogram mass, and in the opposite direction I see a torque from the Fg of the 0.5 kilogram mass. These are the two torques that I see. And if I want to go one step further about what is torque, torque, still 0 Newton meters, is equal to Fg from the 1 kilogram mass times the radius to the 1 kilogram mass minus Fg for the 0.5 kilogram mass times the radius to the 0.5 kilogram mass. And there's a reason I use r as the variable. R is a variable that is reserved for things like circles, distances from the middle of a rotating object, distances from the middle of a circle. Well, I have a circle, or I would have a circle if this thing rotated. Here is the middle of my circle. This is the pivot. This is where, if this thing rotated, it would rotate around. So I'm going to go ahead and make sure that I use R to remind myself that this is R for the 1 kilogram mass. It's the distance from the pivot to the force. And over here, this is R for the 0.5 kilogram mass. It's the distance from the pivot to the force. Be very clear. These are not the distances from the edge of the board to the point. It's from the axis of rotation. It's from the middle of your circle. That's why we call it R. Okay? This is example number 1. Example number 2. I call this one the pirate problem. The pirate problem. Here's what I got. I've got a board, and that board is on a ship like this, okay? It's on the edge of a ship like a plank, like you're walking the plank, matey. And at the edge, you're standing there, all the way over here at the edge. But at the other edge, because this board is not pinned down, there is a mass. And that mass is unknown. We have no idea how much that mass is. But we're trying to figure out how much mass that box needs to be. I'm going to actually fix this picture. How heavy does that mass need to be so that you can go walk to the other edge of the plank without tipping into the water, right? How heavy can it be? There doesn't need to be for rotation or torque to still be 0, okay? So let's think about a couple things. Where is the pivot point going to be? The pivot point is going to be right there. This is where there is clearly tipping happening. There is rotation, or should be, would be rotation about that axis. Let's think about a couple other things. The mass of this person, the mass of you, we'll call it mass of me, is equal to 45.2 kilograms. The mass of the box, I don't know, but I'm obviously going to apply a force, Fg me, on it. The mass of the box is going to apply a big force, Fg, we'll call it Fg question mark. We know that the board itself has mass at the center of mass. Well, there's going to be some force applied right here, Fg from the board. That's all there. Okay. we also know that in order to balance out my downward forces, there must be an upward, let's call it F normal. Is that force going to cause any torques? No, it's at the pivot, so no, that doesn't matter, but it does need to be there so I have balanced forces because this thing is not in free fall, so that's there. Let's think about some other things. Over here we'll write the length of the board is 5.03 meters. This distance here from the mass over to the pivot is 1.60 meters. They told us that in this problem as well. And they're going to tell me that the mass of the board is equal to 11.07 kilograms. Okay, so if you think you got a good understanding of this already, pause the video, go solve it, come back, I'll give you the solution, all right? Otherwise, stick with me. Let's go through this practice problem. Here we go. The first thing I want to do is write my net torque expression. T net. Torque is 0 because there's no change in rotational motion. I'm not tipping in. I want to stay stationary, so it's 0. Let's think about all the forces going this way and all the forces going this way. What would cause it to rotate counterclockwise? Well, I see the torque, not FG, the torque from the FG question mark. I see that force, and I see that force at a distance. That's a torque. That torque is going to cause some rotation, or it could cause some counterclockwise rotation. Let's subtract the torque from FG board. Again, not the force. It's not force that causes this. It's force at a distance. That's a torque. Don't write forces. Minus the torque from me, FG, me. These are the 3 torques that could cause this thing to tip. They need to be balanced. So now let's start plugging some things in. Let's reduce this to different variables. Torque of FG question mark. Well, that's going to be FG question mark times the radius to that question mark minus FG of the board times the radius of the board. And let's do FG me times the distance to me from the pivot. These are all things that we need to take into account. So let's label some things. I know that the whole board, right, the whole board is 5.03, okay? So because of that, I can figure out this, the length to me. Here's the length on the left side of the pivot. The length on the right side of the pivot is 5.03 minus 1.6, and we end up with 3.43. So this length over here, what did I have? I already forgot what I said. I have it written down. I forgot what I said. 3.43 meters. This is R to me. The trickiest one, though, is this one right here. The R to the of the board. Like, where is the center of mass of the board located? Here's how I think about it. I think about this side from the center of the board, center of mass, to the left edge as 1/2 of the length. Okay, that's half of the length. Well, half of the length of this 5.03, right? It's 2.515. Then part of that half length is 1.6. So if I take that, 2.515 and subtract the 1.6 from it, what I'm left with is this 0.915 meters. I'm left with this section right here, half the board minus the left side of the pivot. The right side of the pivot to the center is 0.95 meters. That's probably the trickiest part of this, is like the geometry kind of analysis. But once I get that, and now it's just plug and go. I'm trying to solve for mass, not weight, mass of this box. So let's go mass question mark times G times R question mark. That's 1. Minus mass of the board, which I was given to start, times G, which is constant, times the R of the board, which we just figured out using geometry, minus the mass of me, which I am given, times G, a constant, times the radius to me, or distance from the pivot to me, and I know that as well. Let's start plugging in some numbers. The mass question mark, that's what I'm solving for. Mass question mark times 9.8 meters per second squared, times the radius, which we said was 1.6 meters. There's the first one. Minus the mass of the board, which we learned from the problem was 11.07 kilograms, times 9.8 meters per second squared, times the board. We used algebra to tell us it was 0.915 meters. And then lastly, me, which is 45.2 kilograms, times G, which is a constant, 9.8 meters per second squared, times the distance to me, which is 3.43 meters. I have it. This is all equal to 0 newtons times meters because we're not changing our rotational motion. I go ahead, I solve all of this out, and when I solve all this out, it's equal to 103.23 kilograms, or right around that number, 103 and change, right around there. This is an example of how we can use our understanding of forces and torques to go ahead and solve a net torque problem mathematically. Okay? If you've got questions for me, drop in the chat, send me an email, or ask me in class. But until next time, see ya!